Hey everyone, and welcome back to another video. In this video, we'll be doing a crash course of AP Physics 1, and we'll be starting off by using kinematics. In later videos, we'll go over forces, energy, momentum, simple harmonic motion, and other concepts that commonly appear on the AP Physics exam. Additionally, I'll be creating videos for AP Physics 2 and AP Physics C problems, so make sure you're on the lookout for those videos as well. So yeah, let's get started with AP Physics 1 Kinematics Crash Course. Kinematics is one of the most important and fundamental parts of AP Physics and physics in general. In order to first understand kinematics, we must first understand some important vocabulary. And the first word we're going to be talking about is position. And position is just defined as the location of a certain object. And it can be given in coordinate form. So in 3 dimensions, you can have like something like 1, 2, 3, where 1 would be its x coordinate, 2 would be its y coordinate, and 3 would be its z coordinate. And this would represent the position of a certain object in space. So position just means a location. Next term we're going to be talking about is distance. And most of you guys should also be familiar with distance because it's just the length of a path that someone has traveled. So for example, if some person goes from point A to point B, and this length right here is 20 meters, then the distance the person would have traveled from A to B is 20 meters. That's just the distance that is traveled. And then if it goes from A to B and then back to A, it would be 40 meters because 20 meters to go there and 20 meters to come back. So that's your distance. But now let's talk about displacement. And displacement is going to be your final position minus your original position. So it's going to be your net distance between 2 points. So if we look at the previous example where we have some point A and point B that are a distance of 20 meters apart, and a person travels from point A to point B, well, the displacement from traveling from point A to point B is going to be 20 meters because the final position is a distance of 20 meters from the original position. But if you go from A to B and back to A, the displacement will be 0 because your original position, which is A, and your final position, which is also A, is the same. So the distance between A and A is just 0. And therefore your displacement is going to be 0 if you come back to where you start. Now let's talk about speed. And speed basically just tells you how fast you are traveling a certain distance. And the formula given to find the speed of an object is going to be the distance that the person travels or the object travels over the time it takes. So you're going to divide your distance divided by the time that it takes for the object to travel that certain distance. And the special thing about speed and distance is that both of them are going to be positive. You cannot have a negative distance or negative speed. Now let's talk about velocity. And your velocity is going to be your displacement divided by the time. So it's going to be very similar to your speed, but instead it's going to be your displacement, not distance, displacement over time. And we can see this in the previous examples to see why velocity and speed are different. So let's say that the guy takes 4 seconds to travel from A to B. Then his speed from A to B would be 5 meters per second, which is just 20 divided by 4. And same thing if you go from A to B to A, because then your distance is 40 meters and the time you take is 8 seconds. So it's going to be 5 meters per second. But in the case of displacement, if you go from A to B to A, your displacement is going to be 0 meters divided by 4 seconds. So your velocity is actually going to be 0 meters per second because your displacement is 0. Although you're actually moving, your displacement is going to be 0. And the last one we're going to be talking about is acceleration. And your acceleration is going to be equal to your velocity over your time. Or technically it's going to be the change in velocity, or delta. So this Greek symbol delta means change in. So delta means change in. So in acceleration, it's going to be the change in velocity divided by the change in time. And velocity, we can rewrite this as delta displacement over delta time, because it's actually not going to be your displacement, it's going to be your change in displacement. Same thing for speed, it's going to be change in time. Acceleration tells you how quickly your speed is changing. So it tells you going faster or slowing down. It tells you the rate at which you're getting faster or the rate at which you're getting slower. So quickly before I continue, I'm just going to talk about scalars and vectors. So scalars are going to be a certain value. It's just a certain magnitude. So scalars are just some number. And then your vectors are going to be your magnitude and your direction. So it's going to be a number and also your direction. So which way is it pointing? And we'll look at each of these and determine whether they are a scalar or vector. So first one, position. Position can either, most of the time it's going to be a vector because it's going to be pointing from the origin to where you are located. Your distance is always going to be a scalar. Your distance and speed, both of them are scalars. So there's no direction. It's just going to be a value. Your displacement is going to be a vector. So if you're traveling from point A to point B like this, then you would answer your displacement as the distance, as like the distance between the 2 points, and also the direction at which A to B is. So the direction of the vector from A to B. Similarly, your velocity and your acceleration are also going to be vectors. So most of the time, you don't write your answer as 5 meters per second. If they ask you for the magnitude, then it's fine. But if they're asking you for the velocity, you have to do 5 meters per second and some direction. So 5 meters per second east or something like that, depending on the problem. Same thing for acceleration. It can be like 5 meters per second squared to the east or to the west or something. But these always have directions because they are vectors. So all of these have directions because they're vectors, and your distance and speed are just going to be scalars. So there's no direction. Now let's talk about how we express each of these values mathematically. Normally we express displacement as s. So your s is going to be your displacement. Your velocity is v and your acceleration is a. And your time, so time is going to be t. And most of these are pretty straightforward. So it's just your first letter. Acceleration starts with an A, so you're going to have A. Starts with a V, so you're going to have V. For displacement, it's a bit different. You're just going to have to memorize that displacement is related to an S. Distance is D, and speed is also S. But most of the times, we don't use speed. It's just going to be displacement. And your position is most of the time, it depends. It can be P or X and other things. Displacement can also be X. And since all of these are vectors, you're going to have to draw a little vector thing on the top of a little arrow on the top of each of them, showing that they're vectors. So something like this. Okay, so now that we covered most of the important vocabulary and mathematical symbols for each quantity, let's go over some equations that provide a relationship between these quantities. The first one we're going to be talking about is your velocity. And this is just going to be delta S or for delta T. Remember, delta just means change in. So we can just rewrite this as SF, or the final displacement minus the initial velocity divided by the final time minus the initial time. And for acceleration, we can write this as delta V over delta T. And we can rewrite this as VF minus VI over TF minus TI. Most of the times we can just write this using a delta to show it just means change in. But if you get confused, you can write it as this. So final velocity minus the initial velocity over the final time minus the initial time. Okay, so these are the basic equations. And we can actually combine some of these to get some more complex equations. Complex equations we're going to be talking about are called the kinematic equations. The first one is your final velocity, so v sub f, is equal to your initial velocity, vi, plus your acceleration times the time. And basically, if you know your final velocity and you know your acceleration and time, you can find your initial velocity by plugging your values into this equation. The next one is going to be your distance or your displacement is going to be equal to your initial velocity times the time plus 1/2 times your acceleration times your time squared. And again, this can be used if you know all of these values except for one, and you can solve for that value. The final one is going to be Vf squared, so your final velocity squared is equal to your initial velocity squared plus 2 times your acceleration times your change in distance or displacement. An important thing to note is that all of these require that your acceleration is some constant. If your acceleration is changing, then you're going to have extra terms on each of these equations. For example, on this equation right here, your Vf equals Vi, you're going to have another one that's like 1/2 times Jt squared, where J is jerk, and jerk is basically the change in acceleration. But we're not going to go over that in AP Physics 1, so just assume that whenever we use this, assume that your acceleration is constant. Otherwise, you're not allowed to use these equations. And one last thing I want to cover before we go to some problems is the difference between average velocity and an instantaneous velocity, and similarly for average acceleration and instantaneous acceleration. So average velocity just means the velocity over a certain distance. So if you have a graph of your velocity versus your time, your average velocity is going to be like a period of between a distance of time. So we can describe this as your delta x over delta t. And this is what we're normally going to see in AP Physics 1. But later on, if you're planning to take AP Physics C, you're going to see the instantaneous velocity, and also sometimes in Physics 1. And this basically tells you the velocity at a certain moment in time. So if you had something like this, like some weird graph, the average velocity is you just take this point and this point, and you get your delta x. But your instantaneous velocity tells your velocity at a certain moment. You can find this by taking the slope at that point of the graph. And the way you write this you can't really write this without using calculus. So if you're interested, you can always watch the AP Physics C crash course. But just know that whenever you're finding your velocity, it's actually your average velocity because it's between an actual time period. Your instantaneous velocity is at a certain time. And the same exact thing for your acceleration. So your average acceleration is going to be your delta V over delta T. And this happens during 2 periods of time. But your instantaneous acceleration, so inst is going to be at a certain moment in time. So acceleration and that certain moment. Okay, so feel free to pause the video now if you still need help, or if you have any questions, I can always post them in the comments. And feel free to pause the video to understand and take in some of this information, because now we'll go on to some problems. And these problems are taken from the MIT workbook, and these are problems from past AP exams. So hopefully they should be representative of what you guys see in this year's AP exam. Okay, so the first problem, we have from 1982 and problem B1. So the problem tells us that this should be 10 meters, the problem got cut off. The first 10 meters of a 100-meter dash are covered in 2 seconds by a sprinter that starts at rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity the sprinter had after the 2 seconds. We want to find the sprinter's constant acceleration during the first 2 seconds. And remember, if you look at our kinematic formulas from above, we see that each of these has an acceleration term in it. So we can try looking at each one and see what we know and see if we can plug them into the answer. We know during the first 2 seconds, the distance the guy runs is going to be 10 meters. And we know the time is obviously 2 seconds. And the initial velocity, v sub I, is going to be equal to 0 meters per second because he was started at rest. So let's take a look at our kinematic equations and see which of these kinematic equations can we plug in and solve for solve for A. And if you see, this equation right here works because we can plug in D, we can plug in VI, and we can plug in T, and all we're left with is A, and we can solve for A, our acceleration. So let's do that and see what we get. And plugging in the values, we get 10 meters plus is equal to 0 meters per second times 2 seconds plus 1/2 A times 2 seconds squared. And remember to write your units whenever you're doing these FRQs, because if you don't write your units while you solve, points are going to be taken off. As you can see, we have 0 times 2, which is just 0, so this is just a 0. And now we can just solve for a. So we have 10 meters is equal to 1/2 times a times 4 seconds squared. Because we squared 2 seconds, which gives us 4 seconds squared. And if we solve for a by multiplying both sides by 2 and then dividing by 4, we get that a is equal to 5 meters per second squared. So we can write 5 meters per second right here, 5 meters per second squared. So the next part wants us to find the sprinter's velocity after 2 seconds have elapsed. Now we know that her acceleration a is equal to 5 meters per second squared. And the time t is equal to 2 seconds. And her initial velocity vi is equal to 0 meters per second. If you look at our kinematic equations, we see that if we want to find our VF, so VF equals question mark. And we can see that the equation that we want to use is VF is equal to VI plus AT. So all of our variables are there, we can just plug them in and solve for VF. So if we plug in VF is equal to VI, which is 0 meters per second, plus acceleration, which is 5 meters per second squared, times your time, which is 2 seconds. If we just multiply 5 times 2, which is 10 meters per second, plus 0 meters per second is just 10 meters per second. So our final velocity, or our velocity after 2 seconds have elapsed, is 10 meters per second. Okay, for part C, we want to determine the total time needed to run the 100 meters. We can do this by splitting the run into 2 parts. The part where she's accelerating, so A, and the part when she's at constant velocity, v. And we already know that this is just 2 seconds because it tells us in the problem she's accelerating for 2 seconds. So we're already done for the acceleration part. For the constant velocity part, we know that the distance d equals vt. So the distance is 90 meters, so we can just plug that in. 90 is equal to the velocity, which is just 10 meters per second as we solved before, times the time. And in this case, if we just solve for t by dividing by 10, we get t is equal to 9 seconds. Now we can just add this acceleration to the velocity. So we do 2 plus 9, and we get the total time is 11 seconds. And for the last part, we want to draw the displacement versus time curve of the sprinter. For this, we can just look at the different times and see what happens at each of the times. So we know that for the interval between 0 and 2 seconds, she will have traveled 10 meters. So it's going to be 10 meters right here. And since she's accelerating, whenever we see acceleration on a distance versus time curve, or distance versus time graph, so we have d over here and t over here, the acceleration will always create a parabola like this. It's going to create a curve like that, or like this, or maybe like this. And if it's just at constant velocity, it's just going to be a straight line on the distance versus time graph. So acceleration shows a curve, and velocity just shows a constant line on a distance versus time graph. On a velocity versus time graph, so v and t, if it's constantly accelerating, then it's just going to be a straight line. And if there's constant velocity, it's going to be a horizontal line. And we can kind of see why, right? Because a is equal to, well, a times t is equal to v. So this means that the slope of the graph, or a is equal to v over t. And this just means that the acceleration is going to be the slope of the v versus time graph. So if your acceleration is not 0, you're just going to have a constant line. And the area underneath this curve or this graph is going to be your displacement d. This is because we know that d is equal to v times the time. So just multiplying the axes, we get the area underneath, and that's our displacement. Now let's continue with the problem. So since we have a displacement versus time graph, and it's constantly accelerating, we're going to have a parabolic curve, something like this. It's my best attempt. And now we know that After she accelerates, she's just going to keep running for another 9 seconds. So at 11 seconds, she will have traveled the whole track, or 100 meters, after 11 seconds. And she'll be doing this at constant velocity, or the sprinter will be doing this at constant velocity. So we can just draw a straight line between these 2 points, and that gives us our displacement versus time graph. Or the sprinter initially accelerates from 0 to 2 seconds, and then constant velocity from 2 to 11 seconds, where the sprinter just stops after running 100 meters. So let's go on to another question. And this time it's going to be in 2 directions. Kinematics in 2 directions is basically the same thing as kinematics in 1 direction, because we can just apply kinematic equations on both of the axes, both the x horizontal axis and the vertical axis. And one example of kinematics in 2 dimensions is when you just shoot a ball in a parabolic arc. And let's just quickly examine the forces so it can help us with the bottom problem. Well, we know that there's going to be an acceleration of gravity g downwards. So g is going to be pointing downwards, and it's going to be bringing the initial vertical, so the velocity is going to be split into horizontal and vertical parts. The horizontal part, there's no acceleration in the horizontal direction, so the horizontal velocity stays constant. But the vertical velocity, it's going to start decreasing because there's an acceleration g pointing downwards, so it opposes the velocity, the vertical velocity. So if we just draw the velocities at each point, we see the horizontal velocity is constant, but the vertical velocity is smaller. And then at the very top is just going to have horizontal velocity. There won't be any vertical velocity. And then as we go down, horizontal velocity is the same, but vertical velocity becomes negative, and so on until you reach the ground, where it's basically the same thing as before, except your vertical velocity is just in the opposite direction. And we can just analyze this by looking at in each direction. So we know that the acceleration is 0 in the horizontal direction, and using that we can find the distance it travels if we know the time, so on and so forth. Okay, yeah, so we'll basically use that idea in the next problem. For this problem, we have a ball of mass 0.5 kilograms, which is initially at rest, is kicked towards a fence that is 32 meters away. So this is the ball, this is the fence, the distance is 32 meters, and the height of the fence is 2.5 meters. And it's kicked at an angle of 37 degrees. The nice thing about this angle is just it means that it's a 3, 4, 5 triangle. So we can just split this velocity into 2 components. This is going to be the 3, so it's going to be 12 meters per second. This is going to be our 16 meters per second. So we want to find the time that it takes for the ball to reach the plane of the fence. We want to find after how many seconds will the ball reach this plane right here. We can do this by looking at kinematic equations in the horizontal direction. We know that the acceleration in the horizontal direction, or a sub x, where x means horizontal, is equal to 0, and v sub x is equal to 16 meters per second. Then we know that d is equal to 32 meters. And to find the time, we can use the equation d equals v times t, or t is going to be your distance over your velocity, which is going to be equal to 32 meters over 16 meters per second, which is equal to 2 seconds. So the time that it takes for the ball to reach the fence is 2 seconds. Now we want to find, will the ball hit the fence? If so, how far will it hit? If not, how far above the top of the fence will it pass? And we can do this by finding the vertical height of the ball from the ground at the point when the ball reaches the plane of the fence, or after 2 seconds, which is the time it takes to reach the plane of the fence. We can see how far up the ball is from the ground after 2 seconds and see if that's greater than or less than 2.5 meters. If the ball is more than 2.5 meters above the ground after 2 seconds, then it will go over the fence. Otherwise, it will hit the fence. We can do this by looking at the kinematic equations in the y direction. We know that the acceleration in the y direction is going to be g, which equals 9.8 meters per second squared. And this is going to be negative because it's in the opposite direction. as the velocity of the ball, so it's pointing downwards. Your v sub y, or your velocity in the y direction, is going to be equal to 12 meters per second. Your time is going to be 2 seconds, and we want to find the distance or the height from the ground. And to do this, we can use the equation d is equal to vi times t plus 1/2 at squared. Yeah, we can now plug in the values of vy, ay, and t into the equation and solve for d. If we do this, we get d is equal to 12 meters per second times 2 seconds plus 1/2 times negative 9.8 meters per second squared times 2 seconds squared. Plugging in these values into a calculator, we get this is equal to 4.4 meters. This is obviously greater than 2.5 meters. So this means that the ball will go above the fence, will go over the fence. So yes, it will not hit the fence. So no, how far above will it pass? And we can find how far above it can pass by just subtracting the two heights. If we do that, we get 1.9 meters. So it will go above the fence by 1.9 meters. And obviously, if you're actually taking the test, you have to write all this in complete sentences, but not writing them in complete sentences because obviously I'm not taking the actual test. For the last part, we want to find the horizontal and vertical components of velocity as functions of times until the ball reaches the plane of the fence. So we basically just want to graph this thing until 2 seconds. We want to graph them until 2 seconds because that's when the ball will reach the plane of the fence. So let me just draw this so we know that we graph it until 2 seconds and we don't end up graphing more. We know that our horizontal component is going to start at 16 meters per second, so right here. And there won't be any acceleration in the x direction. So the horizontal component of velocity is going to stay the same. It's not going to change throughout its flight. So it's just going to be a constant line at 16 meters per second. And your vertical component of velocity, well, we're starting at 12 meters per second. And there's going to be a downwards constant acceleration of minus 9.8 meters per second squared. And this is just, remember, this 9.8 meters per second squared is just the acceleration due to the gravity of the Earth. So every object will have this downwards acceleration of 9.8 meters per second squared. And if you remember from like maybe a few minutes ago, we said that the velocity versus time graph, if there is a constant acceleration, the slope of the graph is the acceleration. So this slope right here of this graph is your acceleration. It's just going to be linear. So we want the slope of the graph from this probably to some bottom point to be negative 9.8. And if we draw it, we get something like this. And obviously you can just plug in points into the calculator and see what you get. Like after how much time will the velocity be 0? We can do this using Vf equals Vi plus At. We know that Vi is going to be 12. Your A is negative 9.8. So your time T is going to be approximately equal to 12 divided by 9.8. Which is about 1.22 seconds. And if we graph this, we see it's about here. So it will intersect the x-axis around here, and just have to draw a line connecting those 2 points. And all the way up to 2 seconds, not any more, not any less. So that's it for today's video. Thank you guys for watching, and I'll see you guys later.